For our final topic of today, we're going to do a little bit of foreshadowing into tomorrow, which is differentiability. But we're going to talk about the limit conceptual understanding of differentiability. If you remember, there are 3 qualifications for a function to be differentiable. The first of those is that it has to be continuous. You can't find the slope at a point if the point is not continuous. We talked about continuity already in this lesson. Secondly, your function has to be smooth. You have to be able to put a tangent line at every point, which can't happen if you have sharp edges. You can't figure out where to put your tangent line if you have a sharp edge. And finally, you can't have any vertical tangents. This one's less important to worry about, but graphically, I think the cubic function, or cube root, goes vertical instantaneously, and you can't find the derivative at that point because your slope is undefined. We've already talked about continuity. What I want to talk about next is how to tell if your function is smooth. It turns out that for a function to be smooth, what needs to happen is that the slopes from either side have to be equal. You can clearly see here, that's a sharp point, because from one side you have a negative slope, and the other side you have a positive slope. For a function to be smooth, you have to have slopes that are the same from either direction. We're going to take a look at another piecewise function and try to figure out if our function is differentiable. Remember, the very first thing we need to check for is continuity. So as a review, let's do that. We have a piecewise function. We're trying to figure out if we're differentiable at x equals -1. We're going to start by looking at the limit as x goes to -1 from the left, meaning we're going to look at -2x plus 1. If we plug in -1, we see that that limit is 3. Next, we're going to look at the limit as x goes to -1 from the right. We're going to look at x squared plus 2. We can use direct substitution. -1 squared is 1 plus 2 is 3. And then f of -1 is also 3. So we have a continuous function. As we approach -1 from both sides, we approach a value of 3, and our function is defined there. What we're going to check now is if our function meets at a sharp point or if our function is smooth. And the way we look at that is that we compare the slope as it's approaching -1 from either side. And so we can take the derivative of this piecewise function to look at slope. Remember, slope and derivative go hand in hand. Our slope of -2x plus 1, that derivative is -2. So on the left-hand side, we have a slope of -2. On the right-hand side, we have a slope of 2x, whenever x is greater than -1. And so what we need to do now is look at the limits of these slopes. We can look at the limit as x goes to -1 from the left, meaning we're looking at -2. And if it's always -2, that limit equals -2. We can also look at the limit as x goes to -1 from the right of 2x. If we use direct substitution, that slope is also -2. And because as we approach -1 from either side, our slopes are approaching the same value, we do have a smooth curve. Therefore, f of x is differentiable at x equals -1. And really everywhere, because that was the only point that we were unsure of. I want to draw a quick picture of this so you can see it. We have a line on one side and a parabola on the other. But it just happens that they hit at the exact right point that their slopes are equal at -1. I'm going to try to do a rough sketch of this. We'll see how it turns out. Here, the point we're looking at is -1. We know on the left-hand side, we have a line with the slope of -2. And then right as we hit here, turns into a parabola. And it should be exactly smooth, even though this is a straight line and this is a curvy parabola. But right at -1, they have the same, I guess that's a bad tangent slope, it should follow that line directly. They have the same tangent slope, and it makes a perfectly smooth curve or differentiable on this piecewise function. We'll look at one more example. Again, we have a line and a parabola. We're trying to figure out if we're differentiable at the place where they split apart at x equals 0. I'm going to check first if they're continuous, because if they're not continuous, no way will it be smooth. And I'm going to do that quickly just by plugging in 0. Here we get -2 times 0 plus 1 is 1. Here we get 0 squared plus 1 is 1. Same y value, we're continuous. The interesting thing is to look at their slopes. -2x plus 1, slope of -2. X squared plus 1, slope of 2x on the right side. And now we can look at the limits. So the limit as x goes to 0 of -2, -0 from the left. -2 is -2. And the limit as x goes to 0 from the right of 2x equals 0. These are not equal, meaning that we have competing slopes as we approach 0. Let's draw a picture of that, or let's try to. At 0, from the left, I have a slope of -2. So hitting that right there. But my parabola has a slope of 0 at that point. And you can clearly see this idea of a sharp point there because their slopes are not the same at that point 0. Therefore, even though my function is continuous, f of x is not differentiable. At x equals 0, because their slopes are not the same. I feel that we did not cover this super well over the semester, so hopefully this makes sense. And if it doesn't, feel free to Google more to read more about this or watch a video or email me with questions.